Okay, let's settle down and let's try to go through this.
Okay, so then should I go and get it and then bring it back, or should I just go and talk to the
Okay, let's settle down. Okay, question, yes. Was the mean? The mean on this thing was, again, it's in the ballpark of a 60. It was a 59.84, okay, around where the median was. Okay? Any questions? What was the distribution? Again, the high score was, I think, may have been as high, I don't remember, it may have been as high as like a 96 or a 97. It was a good one. There were there were small numbers in the 80s and the 90s. There were more getting up in the 70s. It's basically a bell-shaped curve with the median around 59. A little bit perhaps higher than the previous midterm, but in the same general ballpark. Any questions about that? When we correlated the previous exams with the current exam, with the previous midterm with this midterm, it came out to be about a 0.6, which is pretty good, okay? Which suggests that the scores are not being assigned randomly on the exams, okay? Any questions about that? Okay, let me go through the exam quickly, the problems quickly. Again, if we graded something wrong, what does it mean to grade something wrong? It means that you had the right answer and we did not give you it. If you had something that was almost the right answer and we took off points, that's what we do, okay? But if there's something that you have a right answer, okay, then I will encourage you to write a note on the paper and give it back to me, okay? And we will take another look at it. Any questions? Okay, so let's go through the problems. The first problem, we'll go through the three big problems. The first problem was on backtracking. It asks for an algorithm that efficiently constructs all, wait, are you, this is good now, right?
Yeah, no, I have to switch the cable out. The cable for the projector.
Okay, one of those cables was mine, so don't take my cable. Okay, good. Thanks. Okay, good. Okay, because there's one for the room. There's one I brought in, and now I'm scared that you're walking off with a cable. So, okay, good. Okay, good. Okay, good. Okay, so what is the problem here? The problem is, first one, backtracking. List all k subsets of n items, okay? For k equals, and basically I give you an example. It means all subsets of exactly k elements, okay, on n items. And I ask you to do it efficiently. And I ask you to do it by breaking it into, describing the solution representation and breaking the work among the three different possibilities. How would I do it to do it efficiently? The most efficient way, the reasonably efficient way, I would set up a solution vector from 1 to k, which is going to have the slots of my thing. Okay? I am going to generate, in general, what are my construct candidates going to do? I want the next, let's say my subset so far is 1. Let's say n equals 7. And I've got 1 in the first spot. Let's say I've got 4 in the first spot. What should be my candidates for the next spot? If I want to do this efficiently, I want to generate each subset once. Okay, that means I should generate them in an order where I don't generate duplicates. Okay? Several people had some ideas of generating permutations or all arrangements of things and generating duplicates. And that's not very efficient. That lost some points. Okay, got some credit, but lost some points. What is the candidates for the next spot? I claim it's the numbers 1 through n. Actually, to be precise, it's the last number, a through I through n. Okay? What should be my candidates? If I want to generate this in lexicographic order, okay, what are my candidates here? My candidates should be any number that is greater than 4. If I have the subset 1 to 4, 5, 7, okay, to generate it once, I want to generate it in a canonical order. So it's not the numbers from 1 through n. It's not the numbers 1 through n minus the ones that are there. I shouldn't be allowed to use any number that is bigger than, that is smaller than the biggest number that is there, which happens to be the last one in my representation. Does everybody kind of get that idea? I am generating them in lexicographic order, okay? And if I do that, I am going to be generating each one once and not n factorial, not k factorial times, okay? Any questions about that? Okay? And again, so the way that I would do it is I would generate my candidates. My vector is going to have exactly k things. I have a solution when I have filled up my vector, okay? And my candidates are going to be all elements greater than or equal to the greater than the last element I put in, okay? And my process solution is I will presumably print it out or something like that. Any questions? There are other ways that you can divvy up the work. Okay, you can use other representations. You can, uh-oh, what did he do? No, that's bad. Okay. Okay, that's bad. You see where that guy, somebody chased back, oh there you are. Okay, it's going to come back, right? Okay, good. Okay, good. Okay, good. Okay, any questions about that? So this is my preferred solution. It is, and there are other ways of breaking the work down, and it got various degrees of credit depending upon how efficient it was, how close it was, how clear it was. Any questions about that? Okay, any questions about other solutions for the first problem? Okay, fair enough. The second problem was having to do with backtracking. Okay, not backtracking, was the dynamic programming problem. And it asks for finding the longest non-decreasing subsequence of a sequence. Okay? So in other words, I'm telling you, I give you a sequence of numbers, and I give you an example here. Let's say the example was 2, 5, 2, 4, 8, 7, 3, 1, 6, 4. This was the example that I gave, right? And I said that what was the longest for this example? This followed by this, followed by, what you call it? Wait, 2, 5, excuse me, it is a 5, right? 2, 5, 2, 8, 7, 3, 1, 6, 4. It said that this was a non-decreasing subsequence. 2, 2, 3, 4. Does everybody see that? Okay. So I ask you first as a warm-up, giving an example, how to find what the longest one is. Okay? That if you understand the algorithm, you should be able to find. Okay? Then I ask you to try to compute a dynamic programming algorithm to try to find what the length of the longest such sequence is. Now this should smell a lot like what problem? Well, if you read the book, there was something in there called basically the longest monotone sequence, where it had to actually be strictly increasing. Okay? All I'm doing is I'm saying I'm allowing you to have ties. Okay? And so basically the same kind of reasoning is going to apply. Okay? I ask you to give me a function, define an English function that will do it, that will be helpful if you could compute it. I say, let's let C sub I is going to be equal to the length of the longest non-decreasing subsequence ending at position I. Okay? So what would that mean? What's the length of the longest sequence ending at this point? Well, that's 1. What's the length of the longest non-decreasing subsequence ending here? 2. What's the length of the longest non-decreasing subsequence ending at this position? It's 2, because you could go 2, 2. In general, what is it going to be? It is going to be 1 longer than the length of a longest decreasing subsequence with a number that is less than or equal to me. Does everybody kind of get that idea? So now what's the length of the one? 5. Well, this thing for 8 is bigger than all of these. Therefore, 8 could go at the end of the biggest of these. If the biggest of these was 2, this could end at 3. 7 is bigger than anything but 8. We have a sequence that can be 1 longer than any sequence ending on these numbers. Does everybody see that? So this one would be of length 3. What's the length of the longest sequence ending at this position? It is going to be 1 longer than the length of the longest sequence ending at a smaller number. I could choose 1, 2, 2. 2 is the biggest of those. There's a 1 of length 3 ending here. Is there any sequence or number smaller than 1? The answer is no. So there's going to be something of length 0 is the base case. This is going to have a sequence of length 1. Do people see what I'm doing here? Okay, and what is this going to be? 6? It's going to be 1 longer than anything that is smaller than 6. I could have it extend by 3. Can't extend the 8, can't extend the 7, but can extend the 3. So there's a way to do it of length 4. Here, let's get up to 4. Is there a way? There's a way to make it 1 longer than this. There's a way of ending in 4. Okay? Does everybody see what function I'm trying to compute? Any questions? Like, what function am I trying to compute? Okay? What would be a recurrence relation for something like this? I claim the following recurrence relation would work. Okay? The answer is something like C sub I is going to be equal to 1 plus the max of C sub j, where j is less than I, and S sub j is less than or equal to S sub j is less than or equal to S sub I. Does everybody see that this is exactly what I was doing to compute this thing? Okay? I'm going to look at all previous values, all j less than I. If you are smaller than the ith element, then you are a candidate to be extended by 1. Okay? If you're less than or equal to this. Okay? And that's what I'm going to do here. Any questions about my recurrence? Okay? Any questions? If you do it this way, what is the running time? Well, it's the number of boxes times the time it takes to fill a box. How many boxes are there? Well, if my sequence is of length n, I've got n boxes. How fast can I fill the box? Well, I have to look at all values j less than I. It would take order n time to check all of these. My claim is that this is going to be an order n squared algorithm. Any questions about this one? If there are questions, look at in the book, the section about where I talk about how to compute these kind of things. The only difference is that this is a less than or equal to instead of a less than. Any questions? Any questions about this one? Okay, good. The last problem asks for a thing called basically to find the minimum bottleneck spanning tree of a graph, weighted graph. How do we define what a bottleneck spanning tree is? Well, it's the one that minimizes the length of the longest edge. The bottleneck is the single longest edge in the thing. Okay? And we want to construct a tree where the single longest edge is small. That is what we're asking about. Okay? And what is the way that I would do it? To ask you to come up with a correct and efficient algorithm and a clear and convincing proof. Okay? What would I do? Well, this should smell a little bit like, gee, we want to use small edges before we use big edges. What algorithm do we have for building trees that uses small edges ahead of big edges? Kruskal's minimum spanning tree algorithm. What does that do? It sorts the edges from smallest to biggest and keeps including them until you have a connected, essentially a connected graph, right? So in fact, Kruskal's algorithm finds this thing. And in fact, that is an argument that in fact any minimum spanning tree, okay, is going to have this property, that it is also going to minimize the length of the longest edge. Okay? Any questions? Yes? Does this work for Prim's algorithm? The answer is Prim's algorithm computes a minimum spanning tree. Kruskal's algorithm computes a minimum spanning tree. Therefore, Prim's algorithm will do the same thing, but you now need to have a proof of correctness. The proof for Kruskal's algorithm is fairly obvious. Okay, we didn't stop including edges in our tree until the graph was connected. There is a proof of, presumably for Prim's algorithm, okay, but it is clearly going to be a messy thing, and if your proof has to be convincing, okay. So there is a way to give a convincing proof of it, and if you got full credit, it was convincing. If you didn't, it was not convincing because the TA wasn't convinced. Any questions about that? Any questions about any of these problems? Yes? What was the runtime for number 3? So there again, there's different. You know, the primary. If I were looking at this, the vanilla flavored version of Kruskal's algorithm that we were talking about was m log m. Okay, so that's usually that's the running time that I would probably be looking for. Any questions? Okay. Anything else? Are we okay, or is this? Okay. Any other questions about the exam? Yes.
Someone hypothetically has a cumulative grade of 80 to 89. What would that letter grade be?
Okay, so let's think. What did I post? I posted the scores. Many of you have seen these things. I also computed a running average of what do we know about you so far. Okay, this is, I think, after homework 3. It includes the grading of the homeworks and up to homework 3, not homework 4, and the 2 midterms. So what does this mean? What do those things mean? I showed you, we posted what that distribution was. You know, I don't want to tell you what each grade means because it means nothing until you finish the rest of the semester, right? But what did I say about grades in here? I said that if you got were average, I said you were going to get what if you were on the median? B minus. What was the median? The median was a 66, if I remember correct. Did I say that in the mail? Okay. The 66, I think, is what the median was. Feeling a little nervous because I suddenly lost my my score distribution to check. But so I don't know where I lost that exactly. I believe that was basically the median. So so what does that mean? That gives you a gross idea, okay, of roughly where you sit. If I took, where was the? Does anyone? No one knows where I put my grading distribution, do you? Because I don't know if this guy took it or anything, or maybe I just. Where did I have this? I had this a minute ago, and I swear it was in my hand, and there's enough papers that have moved around. Okay, my belief was that the median there, that the median was a 66, okay? Yes?
Will peer grading go into, us having done it?
Peer grading is already in there, okay? So your peer grading to date is already in there, yes? That grade was out of 100. That grade is out of 100. Okay. I had thought it was out of 100, with the high grade perhaps being a 91. Okay? But if I remember the distribution, and I'm very sorry, I don't seem to have my... What was I writing on to get these numbers? Does anyone... I did at one point have a piece of paper, correct? Where did that paper go? Does anybody have an idea? I don't think it put it here. Where could it have gone? Okay, if I can make something like that disappear in front of 200 people, I should be a magician. Okay, what is it? No. Ah, yes. Okay, here we go. Sorry. Good. Okay. So what did I have? Yes, the median was a 66 on that. What were the cumulative grade distribution? You know, I'll tell you right now, I'll read it to you. There were 2 people who were 90 or above on the cumulative average. There were 22 people on the 80 or above. There were 80 to 89. There were 59 people between 70 and 79. There were 60 to 69. There were 78. Between 50 and 59, there were 34. Between 40 and 49, there were 11. Between 30 and 39, there were 6. Between 20 and 29, there were 2. So what do you need to know about grades? They will be, again, the median is a B minus. If you got above the median, are you going to fail this course? No. Okay, you hear that. Okay. If you're above the median, are you going to get above the median grade? Yes. Okay. Work that out. The cutoffs where, if you're worrying about am I going to pass, okay, which some people do, I would say the people who are below 50 are the ones I am concerned with. Okay, for the people who need to qualify to graduate, below 50 is where I am now getting nervous. So for those people, you need to figure out something different to do. Okay, any questions? You still have a final. You need to get better on that. Yes.
What are the high-end cutoffs, like for an A and A minus?
They will be decided when I grade them. But again, there's a curve. If you're talking about that, you're probably doing pretty well. Okay. Any questions? Yes.
How will peer grading for homework 5 work?
How will peer grading for homework 5 will work like any other peer grading, as far as I know. Okay, but we'll deal with that later. Yes. We'll deal with that one later. Okay. Any questions? Yes.
We have a particular concern with our own exam. We think we actually did something right, like it was graded wrong.
If you think you did something right and it was graded wrong, you write a note on it saying, my answer to problem X is right. Okay? You then give it to us and we will take a look at it and we will decide that. Okay? And if you're going to do that, I encourage you to do it now. I'm going to have to run very quickly after class today. And we have a speaker in our department that I have to go to, that I encourage anybody who was going to go to office hours, instead go to the speaker in 120 computer science afterwards. But so I won't be in office hours today. If you have something, write up your I am right and get ready to give that to me right after class. Any questions? Any other questions about this? Yes? What? Who is the speaker? The speaker's name happens to be a guy named Hangyang Zhao, and he's talking about a lot of things related to machine learning and data science and interesting stuff. Any questions? Okay. Any other questions about the exam? Okay. Good luck, and we will deal with it. Okay. So what I'd like to do now for the rest of the class is get into what's going to be the final topic for the semester, which is the theory of NP-Completeness. And, again, I've taught this course many times before, and, people have suffered, people are getting tired, people are getting all kinds of things at this point in the semester. Dynamic programming was hard. NP-Completeness, some students, seem to like it. Okay, it's not clear they understand it, but they like it when we talk about this. And the reason is because it is there's a very deep thing going on with NP-Completeness. How many people have ever heard of NP-Completeness? Okay, how many people feel they know what it is? A small number. Okay, that's good. Hopefully more will know after we finish the unit. But, there's something really kind of amazing that's going to go on when we talk about NP-Completeness, is that we're going to talk about how to prove that something doesn't exist. And this is kind of a very difficult thing. How many people believe that unicorns exist? A couple, okay. How many people don't believe unicorns exist? Okay, for the ones that don't believe it, okay, how would you try to prove it to someone who believed otherwise? Yeah? So I've never seen one. Well, saying I've never seen one doesn't cut it as a proof in this class, right? Why is my algorithm correct? I tried to find a counterexample, it didn't exist. Okay, it doesn't, my algorithm's right. Okay, that's really not a proof. How would you prove that something doesn't exist?
Select all known animals and prove that each one of them isn't.
So you go through every place, look every place on the earth and say, is there a unicorn? Okay? And so long as if you really check every place, you got it. But I know no one's checked behind that door. I don't know what's behind there. But there could be a unicorn, right? Does everybody see it? It's hard to conclusively prove something doesn't exist. Okay? What? Double check, if you insist. What is this thing anyway? Okay, good. Okay, no, not yet. Okay, but there's another door out there, and so I didn't go past that other door. Okay. But we're going to be able to use the theory of NP-completeness to prove, and there's a little bit of weasel language here, but I don't want you to get caught up in the weasel language, to prove that fast algorithms don't exist. Okay, and this is kind of an amazing thing. And it's I find a very useful, it's a very practical and useful thing, because suppose you go to a job, okay, and and you are given a task of finding a fast algorithm for some problem, perhaps like the bandwidth problem, and the guy says, our company needs a fast algorithm to find the minimum bandwidth of a graph. Okay, and they send you off to work on it, and you can't come up with one. You can't come up with a polynomial time algorithm for it. Maybe you show them their backtracking thing, and they say, yeah, but it dies on 30 vertices or something like that. Okay? So what can you do? You can report back to the boss, well, I couldn't find an algorithm. I'm too dumb. Okay? Now, what is bad about that? Okay? The boss probably is not impressed, correct? Okay? What would be much better is if you could concretely give them a proof and say, damn it, there is absolutely, provably, no possible way that there can be an algorithm for that problem, fast algorithm for that problem. And if you can do that, that's good, okay? But in fact, proving that there are not fast algorithms is a very hard thing to do. Only once this semester did we actually prove a lower bound on an algorithm. Does an interesting lower bound on an algorithm? Does anyone remember when we did that? Yeah? For comparison-based sorting, right? We could prove that there was no faster comparison-based sorting algorithm. This is essentially the only interesting lower bound known for algorithms. Okay, for an interesting algorithm problem, that there is not a faster way to do it than n log n. And even then, there were weasel words of comparison-based, things like that. So it's hard to come up with proofs that algorithms really can't exist. But the theory of NP-completeness essentially is a proof that algorithms can't exist. And it is a real proof in some sense that although I can't find a fast algorithm, nobody else in the world can find it either. Okay? Now, why is this better than just saying I couldn't find it? It means that they're not going to go try to hire anybody else to do it for you, right? Does everybody see? You can say, yes, I couldn't find the fast algorithm, but Skiena couldn't do it. Okay? Joe Mitchell couldn't do it. Okay? Don Knuth couldn't do it. And you can make a rigorous proof in some sense that nobody in the world knows how to solve this problem and could figure out how to solve this problem. And there's even a stronger guarantees than that. Essentially, what an NP-completeness proof is going to be is, to my mind, for talking about it, a proof that there is a fast algorithm doesn't exist. Any questions about it? And the fact that you can prove these things is really kind of an amazing thing. And the other thing that's kind of amazing is that once you understand how to do it, the techniques are amazing. You know, sometimes there's a two-page, a one-slide idea I'm going to show you every class for the rest of the semester. Okay? And once you understand the one-slide idea, you will be able to see how it works. Okay? Any questions? So again, we've often in this semester encountered hard problems that we couldn't find fast algorithms for. Yes? Oh, that's a good question. What is an objective definition of fast? For our notion of fast, it is going to be that there is a worst-case running time that is polynomial. So an algorithm, you give me an algorithm that is order n squared, that is a polynomial, right? That's fast. If you give me an algorithm that's n cubed, that's a polynomial. That's fast. You give me an algorithm that's n to the 300, that's a polynomial. It's fast. What isn't fast? 2 to the n is an exponent. Exponential. Does everybody agree? 2 to the n is slow. N factorial is slow. Anything that is represented where the worst case running time is a polynomial. N to the 300 log n. N to the 3000 log squared n. Okay, is perfectly fine. Our notion of slow is exponential. Okay? If you gave me an algorithm and said, look, I've got an algorithm that's 1.001 to the n, I would say slow. Okay? Because that's an exponent. Is that right? And there's a little room between these, but let's not get hung up on that. Okay? Polynomial time fast, exponential time slow. Any questions about that? So essentially, an NP-Completeness proof is an argument that there does not exist a polynomial time algorithm in the worst case. Any questions? Okay. And, okay, so let's look at the idea, because there is a one-page idea. This is the idea that I'm going to go through over and over and over again for the next couple of classes. So we've got to start getting used to it. What is the idea here? Suppose I gave you the following algorithm for a problem called Bandersnatch. What is the Bandersnatch problem? Maybe it's that thing the boss hired you to solve. Maybe it's, you know, could it be bandwidth or traveling salesman or whatever. It's a name of an algorithm problem, right? What is the input to the Bandersnatch problem? It's called G. Okay, what is it? Maybe it's a graph, maybe it's a string. You know what it's an input for the problem. The Bandersnatch, this is an algorithm for solving Bandersnatch. And the way it's going to work is, it's going to take the input of the Bandersnatch problem that you give it, the argument, and translate it into the input format expected by a problem called Bobilli. What is Bobilli? It's another algorithm problem. Maybe it's satisfiability, or maybe it's minimum spanning tree, or maybe it's shortest path. I don't know what it is. Okay? But it's an algorithm problem. It's the name of an algorithm problem. And what input does it expect? It expects an input y. Okay? So how are we going to solve Bandersnatch? This particular algorithm is fairly simple. It translates the input of G, the input G, into a specific input for Bandersnatch y, for the Bobilli problem, y. It then calls a Bobilli solver. You go to your library and you say, does my Python library contain a Bobilli solver? Yes, it does. Okay? And it solves Bobilli on y. Okay? And it returns the answer of Bobilli on y as the answer to Bandersnatch of G. Okay? Suppose I give you this algorithm. Let's think again a little bit. It may look like a weird algorithm now, but let's look at it. Okay? Because it is an algorithm, it always returns the right answer to Bandersnatch of G, right? And what it's really saying is that to solve Bandersnatch of G, we do it by translating the input to another format and calling a Bobilli solver on it. Does everybody see that? Could you imagine an algorithm that works like that? You could imagine certain problems, for example, we've talked about using shortest paths to find things, right? You could imagine that basically what do? I take my input, convert it to a shortest path input, a graph, and then call shortest path to solve it. That's the kind of an algorithm that we're looking at here. Okay? So let's say that I have an algorithm like this. Any questions about it? It's got to be doing the translation in a very careful way so that the answer of Bobilli on the translated thing is exactly what we want for Bandersnatch on the original thing. Okay? Any questions about this algorithm? Okay, any questions? Yeah. Bandersnatch is a problem we want to solve. This is an algorithm for solving Bandersnatch. And how does it work? It works by calling a subroutine Bobilli. And in order to solve Bobilli, call Bobilli, you need to have the data properly formatted for Bobilli, right? So we have to translate the input that we gave to Bandersnatch to an appropriate input for Bobilli. Any questions about that? Okay, any questions about what this algorithm is? Okay? Now, I claim that there are two possible things that might be implied by this algorithm. Suppose the Bobilli algorithm runs fast. Suppose I give you a fast Bobilli solver. Okay? What does this imply about how hard it is to solve Bandersnatch? Okay, yeah? Well, it doesn't say that Bandersnatch is as difficult as Bobilli solver. I'm going to say that if there's a fast algorithm for Bobilli, this is a fast algorithm for Bandersnatch. Does everybody kind of get that idea? That if I have a way to do this translation quickly in polynomial time, and there is a Bobilli solver that takes polynomial time, then together this gives me a Bandersnatch solver that takes polynomial time. Does everybody see that? If I have an algorithm for solving whatever problem you care about that calls a shortest path thing, what's the running time for the algorithm to solve the thing you care about? The time it takes to reformat the input, which probably is just like linear or something, and the time it takes to solve shortest path. Does everybody agree? If you have this algorithm and you have a fast Bobilli solver, this gives you a fast Bandersnatch solver. Does everybody see that? What do you have if you have a slow Bobilli algorithm? What does this give you? Gives you a slow what? Okay, what you're saying here is if I gave you a slow Bobilli algorithm, that doesn't mean that Bandersnatch can't be run quickly, but this does give you a slow Bandersnatch algorithm. Does everybody agree? If I give you a fast Bobilli, you get a fast Bandersnatch solver. If I give you a slow Bobilli, you get a slow Bandersnatch solver. But no guarantee that there isn't a better algorithm than that. Does everybody see that? This might be a dumb way to solve it. Okay? But what if instead I tell you that I have a lower bound or a guarantee that there is no fast algorithm for Bandersnatch? Bandersnatch, suppose I can convince you, or I know Bandersnatch is not have a fast algorithm. Bandersnatch is a hard problem. What does this algorithm do? Okay? If I know that Bandersnatch does not have a fast algorithm, and you give me this, what does it prove? I claim it proves that there is not a fast algorithm for Bobilli. Why is that? If there was a fast algorithm for Bobilli, this would be a fast algorithm for Bandersnatch, right? If I tell you that there is absolutely no possible way in the universe, I can prove it, okay? Or I have it on the authority of God, that there is no fast algorithm for Bandersnatch. What does this algorithm show you? It shows you there cannot be a fast algorithm for Bobilli, because if there was a fast algorithm for Bobilli, this would be a fast algorithm for Bandersnatch. Does everybody kind of get that chain of reasoning? This is what we are going to be doing for the rest of the semester, okay? Is just using this. playing out this idea. We're going to have a problem that we know to be hard, which is going to take the role of Bandersnatch. Okay? We're going to have an algorithm we think, I don't think there's a fast algorithm for this. We're going to construct an algorithm for solving Bandersnatch of this flavor. And that will be enough to prove that that mobility problem also does not have a fast algorithm. Any questions about this reasoning here? How many people sort of see it? Any questions about it? Okay? This is the entire idea behind proving problems hard. There's going to be a mother of all problems that we know is hard, and for other problems we care about, be it bandwidth or traveling salesman or any one of other things we've seen, vertex cover, all kinds of other things. If I can get them to play the part of a question that I care about, if I can get it to play the part of mobility, such that I can design a Bandersnatch solver using mobility, if the translation is fast and correct, okay, then this would mean that there is not a fast algorithm for mobility. Any questions about that? That general reasoning here? Any questions? Okay, fair enough. Any other? Yes, question.
Is it proven that the class of problems it can't be solved, or is it just nobody's found a solution?
The way that I will tell you is, again, we'll talk maybe at the last class about what weasel words mean. I don't want you to get hung up on weasel words, okay? The important point is that you will have on the authority of God, okay, or me, or any other computer scientist in the world, that a certain problem is hard, okay? This algorithm is going to prove that mobility is just as hard as that problem I have told you is hard, right? Because if you had a fast way of solving mobility, you had a fast way of solving the problem that we said was hard, okay? And I will detail the weasel wordness later, but I will cut to the chase. To my mind, okay, once you prove that a problem is as hard as the mother of all hard problems, okay, then that problem is as good as hard. There does not exist a fast algorithm for it. Or certainly I'm not going to waste any time looking for it. Any questions about it? It's a rigorous proof that it's time to give up looking for a fast algorithm. Any questions? Yes?
Is there in particular a most common mother of all algorithms?
At the end of class, I will reveal what is the mother of all hard problems. Okay, it's a problem called satisfiability, and we will talk about that then. Okay? Any questions about that? Okay? Fair enough. Any other questions about what I'm saying here? Okay, good. So, now I have a Twitter account which isn't used very much, and I once issued a tweet that I was incredibly proud of. This is the greatest tweet I ever made. Okay? An NP-Completeness proof ensures that a dumb algorithm that is slow isn't a slow algorithm that is dumb. And I don't know if you realize how great that is yet, but we're going to keep looking at this, and hopefully at the end of the semester you'll see why this is a great tweet. Any questions about that? Okay, fair enough. And it does fit in 160 characters or whatever the tweet lets you do. Okay, so let's now talk a little bit more about NP-Completeness. We'll be talking about problems on a more abstract level than we are used to talking about problems in here. So there's a certain amount of formal machinery. How many people have already taken the formal languages course, 303? How many people have already taken it? Did they talk about NP-Completeness in there? Maybe a little bit. Not really. They talked about Turing machines. They talked about the whole theory of NP-Completeness, if you go down to the rigorous, gory details, gets into Turing machines and coding Turing machines and all that. There's a little bit more formality than we need to deal with about what is a problem and stuff like that. It's not going to be that detailed, but I want to make sure we understand that have to be a little bit careful here. First of all, what do I mean by a problem? An algorithm problem, as I think I said on the first day of class, is a general question. Okay? It's something like sorting or the traveling salesman problem. Okay? It is a specification of what legal inputs are and what desired property the answer is, right? What you're seeking to do about it. That is what a problem is. Okay? And so when I talk in here about a problem, recognize that I am talking about, an algorithmic specification at this point. Okay? So what is the traveling salesman problem? You specify an input, it takes a weighted graph, and it specifies the output. What is the output? A tour, a permutation of the vertices that minimizes the sum of the costs, the edge costs in the graph between neighboring vertices in this tour. Does everybody kind of get that? This is a formal specification of the traveling salesman problem. Any question? You specify what is the input, you specify what is the output. Okay? And what is an algorithm? An algorithm is a thing that takes all legal inputs and produces the desired output for all legal inputs. Any questions about that? Okay, so we've been dealing with algorithm problems all semester. This should not be that frightening. I will also talk in here occasionally about instances. What is an instance of a problem? An instance of a problem is an input, okay? So the instance to a problem, an instance is the problem that you're trying to solve, plus whatever input you need to solve it, to solve it on, okay? So what is an input instance to TSP? Well, it's a graph. Does everybody kind of get that idea? And so when we say I have an instance of traveling salesman, you're talking about a specific graph. When you are talking about the problem, you are talking about the formal question. For all possible instances, how do I produce the optimal tour? Any questions about that? Okay. Any questions? Okay. And the solution here, if we wanted to find the minimum cost tour, this was the minimum cost tour, and this is what it cost on that example. Any questions? So we have the idea of a problem, and we have the idea of an instance. Let's see how well we know these definitions. Let's go back to our slide here. What on these slides are problems? Okay, yeah? Bandersnatch and Bobilly are problems. What on here is an instance? Yeah? G and Y are instances. Does everybody see that? What is our translation thing going to do? It's going to translate the instance G for Bandersnatch into an instance Y, okay, for Bobilly. Any questions about it? Now, one thing that's kind of amazing about, if this algorithm is going to be correct, there's kind of a very special property of that translation we needed. For this to be correct, if I'm going to return Bobilly of Y as the answer to Bandersnatch of G, what has to be true if this is a correct algorithm? Okay? Then Bobilly of Y has to be the same answer as Bandersnatch of G. Does everybody see that? It's not just a question of reformatting the problem. Okay, it's easy to take a graph. You tell me that you want to take a graph and reformat it as a string. You could imagine a translation that takes any graph, throws the graph out, and prints out the string Skiena. Okay, but that wouldn't have the desired property. The important thing about this translation is that for this algorithm to be correct, we've got to do the translation between instances in a very, very specific way. So the answer of Bobilly of Y is going to be the same as Bandersnatch of G. Does everybody see that it needs to have that property? Or else this is just nonsense here. Any questions? And you may say, hey, that's got to be a pretty fancy translation, right? Not only is it reformatting the problem, but it is kind of preserving the answer to it. Okay? And that's why the real work we're going to be doing in proving something that is NP-complete is figuring out what is the right translation to be doing. Any questions? Any questions about that? Now, there's one important idea that's going to be necessary to make this translation much, much easier to work with and easier to think about. And that's because we're only going to talk in here for the rest of the semester. I'm now only going to be talking about problems that are called decision problems. A decision problem is a problem that only returns yes or no as an answer. Can anybody think of a problem that is a decision problem? An algorithmic problem that only returns yes or no as an answer? Yeah?
Does this graph have a cycle?
Does this graph have a cycle would be a yes or no question. Does everybody see it? The input is a graph, and if the graph was a tree, you would type no, and if it was not a tree, you would say yes. Does everybody get that? So that would be an example of a decision problem, because the answer is only yes or no. Has anybody ever, any other problems that people have seen? Yeah? Is a string a palindrome? So you may say, well, gee, does it have a cycle or not? That may not sound, but is a string a palindrome? Is a good example. What is a palindrome? It's a string that reads the same forward and backwards. Like what's an example of a palindrome? Okay, one is, I guess, Madam, I'm Adam. Okay, if you look at that, the string reads the same forwards and backwards. Is everybody, you can check that out, is that right? Kabunk, 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 right? Certain strings have this property, certain strings don't. You could imagine a perfectly fair algorithm question. Maybe something for 214, not in this class, right? Given as input a graph, is it a string, is it a palindrome? And the answer would be yes or no. Any questions? Anyone know any other good palindromes? Yes. A race car, my favorite is a man, a plan, a canal, Panama. Okay? Any questions about it? And I believe there was once a book written that is a palindrome. Okay? It's not a very interesting book. But anyway, yes. Any questions? Okay, but the big principle here is, from now on, we're going to only talk about decision problems. Okay? Which are problems that return true or false as an answer. Now, why are we going to care about decision problems? Why is this interesting to us? Well, let's go back to our thing. Why would it be easier to think about things if they are restricted, if Bandersnatch and mobility are both decision problems? What are the possible answers to Bandersnatch? Yeah? True or false, right? What is the answer to mobility? It is true or false. Does everybody agree? So now, when you think about doing this translation, maybe now it doesn't seem quite so hopeless that we can return mobility of y as the answer of Bandersnatch of g. Does everybody kind of see that? Because now this is only going to be a possibility of true and false. The other one is only expecting answers of true and false. If we're dealing with decision problems, we now need to do this translation so that whenever Bandersnatch of g is true, mobility of y is true, and whenever Bandersnatch of g is false, mobility of y is false. Any questions? That's the thing that we really need the translation to do. Still not clear how to do it at all, but now it may seem like a more human task that to preserve, so that the answer to this can be the same as the answer to that. Any questions about it? Okay. So we are only going to talk about decision problems from now on. But I want to assure you that this isn't really a big loss. Okay? That if I had a fast algorithm to solve, I claim that pretty much any of the algorithm problems we've talked about in here, you could solve quickly if you had a fast algorithm to solve the corresponding decision problem. Meaning a problem like traveling salesman or bandwidth or any of the other hard problems we've talked about in here can usually be fairly easily converted from a problem that returns a number to a problem that returns yes, no. So for example, suppose we consider what is the traveling salesman decision problem. This is going to take two arguments. It's going to take a graph, and it's going to take an integer k. And it's going to ask, does there exist a traveling salesman tour of cost less than k? Okay? Think about this problem for a minute. Does this capture really what is hard about traveling salesmen? You're trying to find the cheapest possible traveling salesman tour, am I right? If I gave an algorithm, let's say the weights of the graph were all integers so that we don't have to worry about this real number thing. Okay? But if I gave you an algorithm that could quickly tell for a graph and a k, does there exist a traveling salesman tour of cost less than k? Could we use that to find the cost of the minimum tour? Yeah? Yes? How would we do it?
You can keep increasing k until...
You could start at k equals 1. Is there a tour of weight 1? No. Is there a tour of weight 2? No. Tour of weight 3? No. ... Tour of weight 99? No. Tour of weight 100? Yes. Ding, ding, ding. That's got to be the minimum weight tour. Does everybody see that? So if you have a, a fast algorithm for answering the decision question, that really gives you a fast algorithm for solving the optimization question we care about. Do people kind of believe that? And we can make it faster than what you were doing. Instead of doing, is it 1, 2, 3, what if we do take the total weight of the edges, divide that by 2. Is there a tour of length greater than or equal to this? If yes, move the cutoff one way. If not, move the cutoff other way. Do you see you could use the decision problem as a binary search thing to hone in on where that actual size of the minimum really was more efficiently? How many people see that? I didn't say that so clearly, but I think that should be obvious. Okay? So what is the point of this? The important point here is that if you, that we're going to talk about a theory of decision problems. Every problem from now on is going to be a yes-no problem. But realize deep in your heart that I'm not cheating you. Any problem that we have talked about already can be constructed as a yes-no version. That if I could solve the yes-no version quickly, I could solve the real version you care about quickly. And if I can't solve the yes-no question, well then it's pretty obvious I couldn't solve the real question. Okay? Any questions about it? So from now on we're going to be talking about decision problems, and we're going to be talking about conversions between decision problems using this Bandersnatch-Bobilli idea. Any questions? Okay. Now, what is the mother of all hard problems? Okay, it is a problem called satisfiability. What is satisfiability? Satisfiability is a logic problem, okay, which looks funny at first, but once you get used to it, it's a perfectly reasonable thing to work with. What is satisfiability? It is going to be saying the input is a set of variables, V, and a set of clauses, logic clauses, over V, where the way to read a clause is a subset of variables, and the way to read it is the set of clauses is a logical expression where each clause is going to be this or this, this or this, okay? And the bar on top of it is not. So a satisfiability formula is essentially a logic expression, okay, of the form, for a clause like this, what is my logic expression? It would be V1 or not V2 and not V1 or V2. Does everybody see this logic expression? Okay, let me get rid of my dynamic programming thing. That's history. Okay, so the way that what the input to satisfiability problem is a logical formula over input Boolean variables, where it consists of the form: you've got a bunch of things in a clause are being ORed together. A bunch of things in a clause is being ORed together. And we are taking the AND of all of these things. And we are asking ourselves, is there a set of variables to make this true? Okay? Let's say that you were a presidential candidate who had said a large number of things that some people may not have necessarily believed, and you're now being called onto them. You're trying to say, is there a way that what I said, that it could have been true? Okay? Suppose a particular presidential candidate said this: V1 or not V2, and not V1 or V2. Is there a way that what they said could have been true? Okay? Is there a set of assignments of true or false to V1 or V2 such that this formula can be true? Is there? Yeah? No, I said V1 or not V2 and conjunct not V1 or V2. Is there a way to set V1 and V2 so that this expression is true? Yeah? If I said V1 equals V2 equals true, what happens? True or not true? True or false is what? True. And what is this? Not true, which is false, or true is true. True and true is true. Does everybody agree that if we set the variables V1 to V1, V2, both being equal to true, does everybody agree that's a way to make this statement true? Is there any other way to make this statement true? Yeah? What would be another way? If I said V1 equals V2 equals false, does everybody see that the statement can be made true? Why? We could say false or not false, with meaning true. That's true. And conjunct, okay? Not false, which is true, or false. True or false is true. True and true is true. Does everybody see that there's two different truth assignments to the variables that will satisfy this? We say that a formula is satisfiable if there is a way to set the variables to make it true. Does everybody see that? So this formula is satisfiable. Any questions about what the problem is? Okay? We represent the input, really it's going to be an AND of a lot of OR clauses, right? Each OR clause is specified by a set of variables, and some of which may be negated. Okay? Any questions about it? Let's look at another example. Okay? Suppose we have V1, V2, V1, not V2, not V1. Is there a way to satisfy this thing? Is there a way I can make all of the OR clauses True. That's what I really need to do to make it the and true. All the or clauses have to be true. Right? If I'm going to make all of the or clauses true, what do I know about V1? Does everybody agree my only chance is if V1 is false, right? So if we say that, because if V1, that last clause only has V1, not V1 in it, my only chance to get it right is if I say V1 equals false. But what does that do to the second clause in on it? Okay, if V1 is false, what do we know about V2? Pay attention here, because this is one you now to be able to recall this, because we're going to be using satisfiability. It's the mother of all hard problems. If V1 is false, if we want to satisfy that middle clause, what do we have to do? Yeah? V2 has also got to be false. Because if not, there's no way to take care of the second clause now. And does everybody see that we're screwed now with the first clause? It's doomed to not be satisfiable. It tries, no matter how hard you try, it can't get no satisfaction. Does everybody see that? Any questions about this? Okay? So what is the satisfiability problem? Let's think about it. And let's see if you can give me an algorithm for it. Can anybody here give me an algorithm to solve the satisfiability problem? A correct algorithm. Okay? Yeah?
Take all the variables and do the binary string thing where you assign each one of them to a bit.
So you're saying go through all possible, you're going to say generate all possible n strings of trues and falses. Is that basically right? You're going to say, hey, let's use that backtracking thing that we use to generate all subsets, right? And if we did that, then what's going to happen? There's 2 to the n different possible truth assignments. Does everybody see that? If I give you a particular truth assignment, how much time does it take to tell whether that truth assignment satisfies this? Not much is the right answer. Something like linear time or something like that, right? So it's clear that once I know what the value of V1 and V2 are, I can walk through this and tell me whether it's satisfiable. So what is a correct algorithm? Go through all 2 to the n truth assignments. For each truth assignment, test whether or not it makes the formula true. If it does, report yes. If none of them do, report no. Does everybody see that that's a 2 to the n, probably times n, algorithm for solving satisfiability? What's the problem? Well, it's a correct algorithm, but it's an exponential time algorithm, right? Now, can we get a faster algorithm for satisfiability? It turns out the answer is no, because satisfiability is the mother of all hard problems. Okay? There are good reasons to believe